Snow measurement is of vital importance, especially in arid areas that depend on snowpack in the mountains to sustain life, especially in the valleys. This is the case with the entire Great Basin. And the beginning of our water supply in northern Nevada lies in the Sierra Mountains, which coincidentally is the home of the invention of techniques to measure snow, both snow depth and the amount of water contained in snow. Here are some questions. Where can you find real-time data related to snow depth and snow water equivalent? Another is, which prominent Western University faculty member pioneered snow and snow water equivalent measurement? What are some of the measurement challenges associated with snow depth and snow water equivalent measurement and estimation? And why are standard rain gauges inappropriate for snow measurement? Well, as far as who invented snow measurement and snow measurement techniques, much of the technique and terminology originated with James Church, Dr. James Church, who was a Latin and Greek professor at a prominent Western University. As a matter of fact, it was the University of Nevada, and he developed techniques to estimate water equivalent in snowpack. Here's some photographs of James Church. On the left, he's shown demonstrating the technique that he pioneered for estimating the total amount of water in a snowpack. And on the right, you see him likely on the flank of Mount Rose on one of the many trips that he took from the base to the summit during the middle of the winter. Church Fine Arts Building is named after James Church, and there's an endowment that we manage that was left in his name after he died. Here's an example of some of James Church's notes and some of the development of the technique. The dotted line that you see on the left represents a snow course, which is a series of measurements taken along a line to estimate the total amount of water and the depth of snow across an area. These are translated into measurements of depth, core diameter, and then based on the mass of the snow filled that are in a core, these are translated into not only snow depth, but also into the total amount of water that exists in the snowpack above the soil surface. A variety of state and federal agencies carry out snow surveys in the winter to estimate the total amount of water that will be available during the coming irrigation systems. These are survey slides from the California survey, the Department of Water Resources, carrying out snow surveys in the Sierra Mountains. Here, one of the investigators on skis is pushing a hollow tube down through the snow to not only record the snow depth, but also the mass of the snow inside of the tube. The tube is weighed to record the mass, and the mass is then translated into a total number of...
The reason why we make measurements, number one, at the particular locations and on the particular days, relates to the statistical importance of the data record. It's important that the measurements be made the same location and about approximately the same time each month to maintain that historic record. And it just goes back to when the snow surveys were first started to be done up over the ridge there in Tahoe Basin back around 1906. So we're trying to, basically tie into the historic records that have already been measured. We come up here, we make 5 manual snow course measurements at this location each year, starting on or about January 1st and continuing on to around about May 1st. And the information that we're gathering here is not necessarily today's measurement, but at these locations goes into making the water supply forecasts that are so crucial for effective management of water resources in California.
So the snow surveys are actually accomplished by about 40 agencies. The Department of Water Resources is the clearinghouse for all of that data. but it's mostly measured by local agencies, Forest Service, Park Service, utilities like PG&E, Southern Cal Edison, SMUD, and all that data then is brought together and made available for everyone's use.
As the demand for water resources in California continues to increase, the measurements that are made at this location and many others throughout the Sierra are increasingly important when it comes to determining water allocations, environmental criteria, and a number of other factors in terms of water management within the state. It's one of the tools that we can use that is the most cost-effective in terms of maximizing our water resources.
Measurements are also done with automated systems operated by the Natural Resources Conservation Service at their SNOTEL sites. A typical SNOTEL installation looks like this one. It has an instrument shack that holds data loggers that collect impulses from giant snow pillows or big snow pillows that are filled with antifreeze that lie outside of the snow shed. There are also instruments, sonar emitters and receivers that emit impulses to estimate the depth of the total snowpack at that point as well. This does away with the need for carrying out manual snow surveys and provides good information based on the pressure on the hypalon pillows, these massive pillows that are out there. Pressure is translated by voltage, by pressure transducers, into an estimated amount of water at this point. The envelopes are durable, made of stainless steel or synthetic rubber, and they contain an antifreeze solution. And snow water equivalent, or SWE, is calculated by measuring the pressure exerted on these pillows by the weight of the snow. Snowpack telemetry is managed and maintained by the Natural Resources Conservation Service, and the purpose is to measure snowpack in the mountains of the West and forecast water supply. There are 600 sites in 13 western states. They're equipped with snow pillows, storage precipitation gauges, air and temperature sensors, and then sonar sensors to estimate the total depth of snow at these sites. They record data at 15-minute intervals. And here are some of the states, all of the states that actually have data associated with, or that are collected from the system. And here's a typical system, a photograph. In the background we see the brown instrument shack. The pipe with the fringe on it is our precipitation accumulation gauge. The L-shaped bracket just to the left of the precipitation accumulation gauge has a sonar sensor and emitter at the very top that's used to sense snowpack depth. And then below, in this graveled area, we have the hypalon pillow on which the snow accumulates and exerts a pressure that can then be translated as a voltage into a snow water equivalence at that site. In the immediate vicinity, we have many SNOTEL sites. Directly to the west in California, we have 3 on the border with California that I'll look at in a minute. Again, these are accessible through the internet, through the SNOTEL gateway, and can be used to report the depth of snow and the amount of snow water equivalents at each one of these sites. Not coincidentally, in Nevada, all of the SNOTEL sites are located on ridgetops above the valleys that are sustained by the snowpack that accumulates on those ridgetops. Here's an example of some of the data that are collected. We have in the red line accumulated precipitation, and you note that it steps up and never steps down. And that's because it's reporting at the end of the year in this case 2011 on August 31st, the amount of precipitation, the cumulative amount of precipitation that's been received from the beginning of the water year until whatever the ending date of the report is. We can also see the amount of water that's included in the snowpack, and you can see that in this case the amount peaks around the 28th of April. It begins to be recorded in late September or early October, peaks around the 28th of April in 2011, and then rapidly drops off as the months become warmer until at the end of June we have no water in the snowpack at all at this site. So let's compare this with standard climate stations. First of all, the openings in standard rain gauges freeze and snow accumulates and cannot be measured. So standard rain gauges are a very poor way of estimating the total or measuring the total amount of snowfall that occurs, in part because we're measuring solid water rather than liquid water, and the liquid water can't actually enter the gauge because of the freezing and accumulation at the top. Another thing is that snow falls in many different directions, so we lose a lot from blowing and turbulence above the gauge. Also, the distribution of snow is heavily affected by wind currents and obstacles, for example trees and buildings, which leads to high spatial variation and unclear representation from point measurements. What this simply means is that when we measure snow at a certain point, it may not be at all representative of snow even a few feet to the left or right of the point that we've chosen for measurement. You've seen this if you've ever fallen into a snowdrift out of an area of relatively shallow snow. So back to our questions. Where can you find real-time data related to snow depth and snow water equivalent? You can find that by visiting the SNOTEL sites that are maintained by the Natural Resources Conservation Service and by going through the SNOTEL gateway that they maintain. The answer to this is James E. Church, who is a professor of Latin and Greek at the University of Nevada, and who also, in his spare time, pioneered snow and snow water equivalent measurement. Some of the challenges associated with snow depth and snow water equivalent measurement include difficulty with measurement techniques, standard rain gauges are poor ways of measuring snow depth or do not measure snow depth and have a very difficult time actually accounting for snow water equivalent, in part because of freezing and accumulation of snow outside of the gauges. And some of the other measurement challenges include coming up with a spatially representative value for snow depth, which is why the SNOTEL systems are expensive and also why they've been designed to provide data from specific points to answer a specific question which is related to water supply in the western United States.